In 1928, a pound of cemented tungsten carbide cost $48. It was the hardest cutting material in industrial production and could machine steel at speeds that would destroy high-speed steel in seconds. Yet General Electric and Germany's Friedrich Krupp signed a 15-year pact to control the supply. Within a few years, the price rose to $453 a pound, even though the actual production cost was only a few cents per gram. American machine shops were forced to keep using slower, high-speed steel because two corporations decided the future of metalworking was too profitable to share. Then a metallurgist in Latrobe, Pennsylvania, found a way around the monopoly. Philip McKenna was born in 1897 in Pittsburgh into a family where metallurgy was almost a family religion. His father, Alexander McKenna, had developed an 18% tungsten tool steel that dramatically increased cutting speed. The family's metalworking roots went back to 1832 when Philip's grandfather, an Irish coppersmith, founded the McKenna Brothers Brass Company. Philip grew up around forge fires and heat-treated drill steels. By age 15, he was working with chemists. By 18, he already held patents for tungsten extraction and cobalt separation. He was a professional chemist before he was old enough to vote. McKenna studied at George Washington University while working days in research. He had already been an assistant at the U.S. Bureau of Standards, and later he attended Columbia as well. But his career took shape in western Pennsylvania. In 1910, the family had helped organize the Vanadium Alloys Steel Company, later known as Vasco, in Latrobe, a railroad town southeast of Pittsburgh that had become a center of alloy steel production. By 1928, Philip moved there to become Vasco's research director. For the next decade, he focused on one enormous problem: how to cut steel faster, harder, and longer without burning through tools. He experimented with cemented carbide formulas, searching for a composition that could outperform the market. In December 1937, he filed a patent for a tungsten titanium carbide alloy. It was granted in April 1938 and described as harder than the hardest tool steel. McKenna called it Kennametal. That same year, after a bitter dispute over a troubled carbide venture, he resigned from Vasco and started the McKenna Metals Company in Latrobe as a sole proprietorship with about a dozen employees. Latrobe was the right place for him. It was a town built on metallurgy, with alloy steel plants and tool steel shops nearby. Half the people knew what he was trying to do because they worked with metal for a living. But McKenna was walking into a cartel, not a free market. In 1928, GE and Krupp had signed a sweeping agreement dividing the global cemented carbide market between them. Krupp would not export to the United States. GE would not export without Krupp's consent. They cross-licensed patents, limited competitors, and kept prices high. The markup was obscene. GE's own carbide sold for $453 a pound, or about $1 per gram, even though the production cost was a fraction of that. The reason mattered. Carbide tooling could last hundreds of times longer than conventional tool steel, but shops could not afford the price. So machinists were forced to keep using slower cutters and lose productivity. The cartel's power depended on keeping the bottleneck in place. McKenna's tungsten titanium carbide got around the patent wall because it was different enough to avoid their claims, and his pricing was competitive. The cartel tried to pressure him into joining their licensing structure, but he refused. By the early 1940s, the monopoly had become so notorious that it drew Senate attention. Hearings condemned the shortage of this essential material. The Justice Department indicted GE, Carbolloy, and their officers in 1941 for antitrust violations. The case was delayed by the war and eventually decided in 1948 when Judge John C. Knox ruled that competitors had been excluded by purchase, boycott, and market division. The fines were small, but the monopoly was broken. McKenna did not need the headlines. He needed orders, and by the time the case was decided, he already had them. The company began with about $30,000 in first-year sales. By 1941, it had taken in large international orders through Lend-Lease and contracts from the Chrysler Tank Arsenal and U.S. Steel Export. Sales approached $1 million. The shop in Latrobe had become a strategic supplier during World War II. Kennametal's carbide tools were essential to wartime manufacturing. Tanks, aircraft engines, and artillery barrels all required precision machining of hardened steel at brutal production rates. Carbide tooling made those speeds possible. The company also developed tungsten carbide penetrators for armor-piercing shells. These were not accessories, they were munitions. McKenna was shipping them from Latrobe to ordnance plants and watching them leave in transport ships. In 1943, Philip dissolved the family partnership and incorporated Kennametal. Revenue had reached $7.5 million. After the war, when defense work disappeared overnight, the company shifted to a new innovation that would change machine shops around the world, the Kendex system. Introduced in 1946, it used mechanically held, precision-ground indexable carbide inserts. Before indexable inserts, carbide tools were brazed onto steel holders. When the edge wore out, the whole tool had to be reground, which changed the geometry and tied the machine up while a skilled grinder worked on it. Kendex changed everything. A machinist could loosen a clamp screw, rotate the insert to a fresh edge, and keep cutting in less than a minute. When all the edges were worn, the insert was thrown away and replaced. The holder lasted indefinitely. That idea became the template for modern machining, the first throwaway insert era. The Korean War brought Kennametal back into defense work. The Department of Defense ordered 190,000 armor-piercing tungsten carbide penetrators. Sales climbed steadily, and by 1954 they had reached $24 million. In 1958, Kennametal created an overseas corporation to formalize its international expansion, including ties in Italy and joint ventures in Britain. The company was no longer a regional metallurgical shop. It was becoming a systems supplier for an increasingly global industrial base. McKenna died in 1969 at age 72 after a career that had earned him recognition from the American scientific and engineering community. Outside the lab, he was also deeply involved in monetary policy and chaired the Gold Standard League for several years. He believed that we're just starting to realize the possibilities, and he lived as if engineering could keep finding new ones. After his death, the company kept growing under family leadership, but the next chapters would be global, not local. In 2002, Kennametal acquired the Whittier Group from Cincinnati Millicron for about $170 million. Whittier had begun as a Krupp brand in Germany, so the company that had broken the cartel now owned one of the cartel's old names. McKenna had been gone for decades, but the irony would have pleased him. In 2005, Kennametal bought Extrude Hone, a company famous for abrasive flow machining, or AFM. In AFM, a polymer medium loaded with abrasive grit is forced through internal passages under high pressure. The medium conforms to every contour and removes material uniformly from surfaces that ordinary tools cannot reach. The process is used to polish turbine blade cooling passages, fuel injector bodies, and hydraulic valve intersections. It became so widely used that extrude hone started showing up as a verb in engineering circles. In 2012, Kennametal added Deloro Stellite, bringing cobalt chromium superalloys into the portfolio. Stellite had a long history in extreme wear applications, and the Belleville, Ontario plant that came with the deal had been producing those alloys for decades. For workers there, it was not just an acquisition. It was a trade and a community. Kennametal's own manufacturing is built on powder metallurgy. Tungsten carbide powder is blended with cobalt or nickel binder, pressed or extruded into blanks, sintered, then ground to final geometry and coated with wear-resistant layers such as titanium aluminum nitride. The company also produces carbide rod blanks and continues to invest in recycling programs that recover tungsten and cobalt from spent tools. That makes the business cyclical in a very particular way. It depends on extraction, precision forming, finishing, and reclamation all at once. As Kennametal expanded into a nearly 100-country operation with thousands of employees, tensions with labor became harder to ignore. In 2017, the Belleville plant, which had enjoyed decades of labor peace, faced a sharp contract fight over wages, overtime, and concessions. A strike mandate passed overwhelmingly. 2 years later, the Greenfield, Massachusetts plant, unionized since 1941, walked out over healthcare and staffing demands. The company later closed Greenfield as part of a footprint restructuring. The environmental record was another reckoning. Heavy metal processing created hazardous waste that old industrial practices handled badly. Sites linked to tungsten and carbide work ended up on Superfund lists, and Kennametal became one of several corporations named in cleanup actions. That legacy is part of the cost of making hard materials at industrial scale. At the same time, the company has tried to reinvent itself for newer industries. It has invested in additive manufacturing, built lighter 3D printed tools for electric vehicle production, and used redesigned stator bore tools and transmission housing tools to reduce weight and machining time. These are not prototypes, they are running in production. The materials have changed, but the underlying job remains familiar. Remove metal where it is not needed and leave behind a part that can survive heat, load, and repetition. Kennametal's broader significance is that it helped turn cutting tool strategy into a science of systems. Its inserts, grades, coatings, and tool geometries are all designed to work together rather than as isolated products. A shop buying a Kennametal solution is not just buying a bit of carbide. It is buying speed, tool life, predictability, and a way to keep machine uptime high when labor is expensive and tolerances are tight. The point of Kennametal's story is not just that one man broke a monopoly. It is that he changed how machining worked. His carbide made it possible to cut faster and longer. His indexable insert system ended the era of constant regrinding and changed every shop that adopted it. His company survived him, absorbed competitors, entered new materials, and kept evolving in ways he could not have imagined. Today, Kennametal operates in nearly 100 countries and continues to make tools, coatings, and engineered materials that push industrial production forward. The monopoly that tried to stop Philip McKenna is gone. The company he built outlived it, and the industry still runs on the logic he helped create. If the cutter is strong enough, the whole factory can move faster. The deeper legacy is that Kennametal taught manufacturers to think about the tool itself as a competitive advantage. Before that shift, the cutter was often treated as a consumable, a necessary expense between the machine and the part. McKenna's work made the cutter a strategic object. Better carbide meant higher speeds, better finishes, fewer stoppages, and a direct effect on cost per part. That changed purchasing decisions all the way up the chain. It also changed the way engineers talked about wear. Instead of accepting dull tools as the price of doing business, shops started treating tool life as something to be extended, measured, and optimized. That mindset now governs modern machining just as much as the raw material does. Kennametal helped make that philosophy normal. There's a final irony in the company's arc. McKenna began by escaping a world where two giants controlled a scarce material and charged what they pleased. He ended as the founder of a company that itself became global, diversified, and indispensable to the world's hardest cutting jobs. The monopoly is gone, but the idea that a better tool changes the whole factory remains. That is the story of Kennametal, a metallurgist's answer to a cartel, a family company turned global supplier, and a reminder that a breakthrough in cutting metal can reshape the entire industrial economy. Kennametal's reach also grew because industrial customers do not buy cutting tools the way consumers buy finished products. They buy them as part of a production system, and that means trust matters as much as the chemistry of the carbide. A tool that lasts longer, cuts faster, or leaves a cleaner surface can affect everything downstream. Cycle time, scrap rate, machine uptime, and even the amount of energy a factory consumes per finished part. That is why the company's products spread so widely after the war. They made complex machining economically easier, not just technically possible. The company also learned to serve industries where failure is expensive. Aerospace components, medical parts, and precision automotive pieces all punish inconsistency. Kennametal's coatings, inserts, and advanced tool geometries fit those sectors because the value proposition is not only speed, it is repeatability under stress. If a tool behaves the same way every time, a plant can plan around it. Latrobe, where the company began, remained symbolic long after the business went global. It was a place where alloy steel, tool making, and practical metallurgy already had roots, so McKenna's work could grow out of local knowledge instead of fighting it. The town gave him the vocabulary of heat treatment, wear, and cutting performance before he ever built a company. Later, the company returned the favor by making Latrobe a point of reference in the history of hard materials. Another reason Kennametal endured is that it never treated the cutting edge as a static thing. It had to keep adjusting to new alloys, new machine tools, and new production expectations. That forced the company to move between chemistry, metallurgy, and manufacturing practice. In that sense, Kennametal became more than a supplier. It became part of the language of production itself. That is what made it hard to replace. So the legacy is broader than one patent or one company. McKenna helped industrialize a new way of thinking about metal removal, one that treated hardness not as an obstacle, but as a design problem. The company that followed him kept turning that insight into products for decades, and the industries that use them still depend on the same logic today.